Hello everyone. Any question from the last session that we had? Anyway, today I want to talk about the optimum receiver for continuous phase modulation over AWGN channel as a very useful special case. We investigate the GMSK Gaussian minimum shift gain receiver. We have talked about the transmitter and how heal the low-pass transmitted signal, and now we want to talk about the receiver over AWGN channel. Okay, let me give you an overview about the optimum receiver for modulation with memory. We have talked that the maximum likelihood sequence detection is the optimum receiver when you need to decide on each of the symbols for each of the received sample. If the length of the received sequence of samples are n, you need to decide on all of the possible transmitted symbol, which is not a very easy task. Then we introduce the Viterbi algorithm and the Mlsd diagram for overcome to the problem. We mentioned that for a sequence of n received sample, the Mlsd diagram has n steps. Each step has m to the power of L minus 1 state, where L is the length of the applied filter to the transmitted signal. We have solved an example actually with 2 taps of filter, and we saw that the length of the step was 2 to the power 2 minus 1, 2 actually. One of the most important problems with the CPM signal is the length of the filter that we have applied is infinite. The phase of the produced phase at step n is actually related to the transmitted symbol of the first transmitted symbol I0. And now we want to see how we can solve this problem, because if we want to go from m to the power of L minus 1, again, 2 complexity to solve. We also mentioned that each branch indicates an outcome with a transmission of S of m, which is possible symbol, transmitted symbols, which here and at the solved the example, we saw that it is probably 1 or minus 1 even for the GMSK signal, or for the other kind of modulation it differs. Each state has m input branches. A very important case, very important point. Each state has m input branches because we have m symbol, therefore m input branches, but we cannot just accept only one. We need to find the winner branch with the minimum cost, with the minimum weight, delete the others, and go forward to the next step. Therefore, we need also weight matrices of each of the states at each step. Let's call it the W of M and K, which M introduce the index of state, and K denotes the index of step. And we have seen something like this, the equation that gives you how to find the weight of a state. You have m of these for each state as input outcomes of the state, and you just need to find the winner, which is the minimum one, and consider that the weight is equal to the weight of the winner branch. Okay, what was the CPM modulation? We mentioned that the low-pass signal S is the cosine of the phi of t and I plus j sine of the phi of t and I. or we can mention it as a e to the power of j phi, where phi is a continuous also, but we mentioned that we can sample it over the sample version of q of t. It's a summation of k is equal to 0 to n and so on and so on. This was the main equation for the CPM signaling, but for a special case that we have solved, we saw that for the GMSK, h is 1 over 2, L is 3t, and qt is equal to, again, 1 over 2 for t is greater than L. And we saw that we can divide the phi of t and I to two different parts. P, summation from k is equal to n minus 2 to n ikq of t minus kt. This part, and plus the other, the second part, which is actually is just a function of transmitted symbols. Because after the q of t for t is greater than 3t is constant, therefore the second part is just a function of ik. But let me give you a general form for consideration of the CPM modulation. When L is uppercase K or T, could be 1, 2. At your book you have an example of the CPM receiver for k is equal to 2. Here for the GMSK k is equal to 3. But you can also consider 1, 5, whatever. In this case, again, you can divide it, the main formula of the GMSK signal into two parts. For understanding, the point that we are dividing the phi of t to two parts is because we need to somehow handle the number of state diagram, the Trellis diagram, the state of the Trellis diagram. Because as mentioned, when you apply the filter of length L, the number of the state must be m to the power L minus 1. But here, as you can see, the q of t as a filter is from 0 to whatever you are. It's infinite length. Then we need to do something. The point is that we can divide the phi of t and I to two parts. This part is not a function of q. Therefore, if you look at this part and name it as a theta, you will see in the future that this is something with actually this part and that part. Each of these two have actually limited variable. I mean, the possible value that they can be actually is limited. We will see in the next slide what does it mean. Okay, here you can see that the first part, which we call it theta of t and I, as a function of ik and q of t minus kt. We know what is the q, therefore no problem. We know what is h, we know what is the k with a straight uppercase. Therefore, we can say that it is a function of I n minus k plus 1 through the in. Okay, suppose that the k is 3, this uppercase k. Therefore, the possible value of n is, and when the ik is within the space of the transmitted symbol, the total number of possible value for this is m to the power of k. Consider case 3, and ik could be either plus or minus 1, GMSK. Then all possible value for the first one is 8 as a function of S1, S2, and S1 and S2 as a function of I n minus 2, I n minus 1, and I n. Okay, what about this one? Any idea? When actually, there's a function of h. When h is 1 over 2 or half, how many possible value? 4. 0, pi over 2, minus pi over 2, and pi. Therefore, it's actually, but the point is that it's a function of ik and also a function of h. Let me, it's not infinite actually. When the h is, you know that it's the 4 cases, but suppose that h is 3 over 4. You know, the CPM signaling, actually the GMSK receiver, it's a little bit complex. I cannot give you an example or ask you a question at the exam, but this points, the number of a state is important for you to know for exam too. Because if someone is going to ask you, suppose that you are in the interview, you are claiming that I am familiar with the GMSK signaling, CPM signaling. They are not asking you about that. Okay, come on, solve this problem for me. They're asking about these details. Okay? You need to understand how to come up with the number of the state of the Viterbi diagram for the CPM signaling. Over the GMSK, over the fading channel. We will maybe, I don't know, discuss too. Anyway, what are the possible value of this part, considering that the ik is plus or either minus 1, but the h is 3 over 4. It's exactly the, you just need to calculate it. When a symbol comes inside, how much phase it will be added? Pi, it's pi 3 over 4 ik, which would be 3 pi over 4 for ik is equal to 1, or minus 3, 4 for ik is equal to minus 1. And you just need to start from here, from 0, because for some value it's 0 at this start.
So it's,
and now you can go up for this value, then rotate, then rotate. For example, here there will be something like this. You may come back to the 0 or go for 6 pi, which is this one. When you are here, then you can go for this one. When you're here, you can go for this one. When you're here, you can go for this one. And when you are here, you can go for this one. And finally, when you are here, you can go repeat it that way. Not 0 again. The 0, 1 is for the first one. It's not will be repeated again. Or maybe.
yeah, it can be.
It can be from this one to this one, or maybe this one for.
Yeah, I think pi is also possible.
Yes, pi is also possible. Yes. 1, 2, 3, 4, 5, 6, 7, 8. That's right. Yes. Then this part, the number of a possible value for this is important. You will see how it rules at the Viterbi diagram and the construction of the number of a state of the Viterbi diagram. Okay. Therefore, the total number of possible value for the phase, the phi of t and I, will be determined by the possible value of theta of t and I, the first part, and the theta of n, which is the second part. This value is the total number of states at each step. for the GMSK signaling, we have 8 possible values for theta of T and I, and also 4 possible values for theta of N. Therefore, 32 state for the return diagram.
So when designing our transmitter part in our project, we have to use this formula, or we can
Not
use
actually. The only things for the transmitter that you need is the GMSK phase formula that we have here, this one.
the main one.
This is something that you need to go for the transmitter. That's
Yes, I try to do that with the second line.
second line is actually fine, but the point is that
Will it make any difference while making?
the difference is if you go for this one, suppose that you are at the state 1000 for the 1000th transmitted symbol, you need to again, okay, go on and add IK
Yes.
from 0 to I don't know. Again, add these two all together, but you do not need to do that. Start from 0 after you came here, because for k is equal to 0, 1, and 2, you do not have any theta in here. For the third one, for k is equal to 3, you say that, okay, what was this one? If it was plus, your phase is pi over 2. If it was minus 1, your phase is minus pi over 2. Okay? Then, again, for k is equal to 4, it was your phase. The most important point is here. It will be go, this one, will be go to, for plus 1 to pi, and it will go to 0 for minus 1. It means that you just need, if it was plus, just add pi over 2 to the phase. If the incoming, this is the incoming for k minus 1 for this one, and minus 3. If you, whatever your theta is, just plus a plus, when I minus 3 is 1, or minus pi over 2 for I and this 3 is minus 1. Just plus or minus. You do not need to go again at the start 1000 at this state, again sum from 0 to 997. Do not need to do that. Just go some kind of Markov process. Go pi over 2 to the forward or minus pi over 2 backward. This. And we need this point. It's very important to understand it for the Viterbi diagram. Because you will see that, and I don't want to confuse you, we will talk about this one. But the way that, yes, this is the way that you need to calculate. This one, calculation of this one is very fine. It's a function of 3. You have the IK, you calculate this one, and also you calculate this one. Add them together, and just e to the j5 gives your transmitted symbol. Okay.
We will be using the values of theta n for designing the receiver part. So the particular values of theta n, because in the second line we don't get theta n and theta, right?
You mean
no,
this one?
The second one.
This one?
Yeah.
Actually, this one is come from this.
Yeah.
Okay.
Yeah, I got that. This theta n.
Okay, this one?
Particularly. Will that be used to demodulate?
Actually, the concept will be used. We want to discuss that how many possible value this one has, and based on the possible value of this one, you need to construct the Viterbi diagram. If this one, I explained to you, if this one the total number of the Viterbi diagram is the non-possible value of this one, which is the function of k. But this one is the function of this one and h2. Therefore, we discussed that the total possible number of Viterbi diagram, okay, different state number for different m, h, and k. Whatever your CPM signaling is, the Viterbi diagram that you need, the trellis diagram, is the number of states is a function of this. This one, and let me see, this one make the total number of the first one. This one and this one makes the total number of the second part, theta n. Okay, but the point is, the GMSK trellis diagram will have 32 states, that's fine. But for k is equal or greater than 5, we will see that. Why? For k is equal to lower than 4, you're doing as follows. Let me just explain something to you before. You know, this is not the only way that you can implement the trellis diagram or implement the Viterbi algorithm for the CPM signaling or whatever. Maybe you can go for the lower number of states, but on that case you need to do much more programming, complicated. It is the simplest way. I will explain the point here. But here in this concept, nothing is extra. Okay, everything is completely fine, and you will see how. For k is equal to 1 and 2, you're starting for k is equal to 1 here, and go for here. At the first step, k is equal to 1, you need to calculate the W11 and W21. How we calculate W11? What is W11? What is? Give me a little help. Just remember the maximum likelihood sequence detection. I want to compare that with you, with this one. This one, for the maximum likelihood sequence detection that we have, suppose that the IK is either plus or minus 1, and R of k was IK plus IK minus, let's call it, let's say, exactly the same example that we had last time. Okay? What was the W11? Remember? W11 was the distance between the first received symbol, and because the S1 is for this and S2 for this one, this is the transmitted, I call it the system model, but it's the model of the transmission. You need to go forward. I am not putting S1 here because we have transmitted this one. I need to put, remember? Or whatever. Am I right? And W21 was R1 minus half of this one. S2, sorry. Am I right? Everyone are following? Okay. Then, okay, what is the W11 for here? That will be R1 minus what? Okay, what is S1?
Oh,
Based on this S1, okay, you cannot say, okay,
oh,
this one is wrong. If you say W1 minus S1 is wrong, because S1 is 1, S2 is minus 1. Okay? S1, S2. Hey. S1 and S2. Then what would be W11?
R1 minus 1.
R1. No, not for here.
Oh.
For the GMSK signaling. Okay,
Oh.
you have 1 to transmit. Are you transmitting 1 or something else? What you are transmitting for the GMSK signaling? You are at the first step, you have 1 to transmit. What you transmitting? You're transmitting e to the j phi, where phi is 2 pi h, summation, no summation here. The first step, I0, q of 1. H is half. It goes from I0, K1, Q1, sorry. Then what is your transmitted symbol? Is this J pi I0, Q1. Then what is the W11? You have transmitted this one. The weight is the distance between the transmitted symbol and the received symbol. Therefore, W11 is R1 minus S1, and S2 is the lowercase, when S1 is the e to the j pi. What is the I0? For the first one, do nothing. And for the second one, because you are transmitting the minus 1, is the minus j pi q1. First step of the vector video for the GMSK signal. Okay, you have this one, that's fine, you have this one, great. Look at this. Let's go back to the example that we have. Last session. Then we need to go for the next step. But the point is here, you cannot go something like this. Because we do not need to know actually tree of symbol, tree recent symbol, and the theta of n. We go forward, we expand the vector diagram until we can distinguish what was this one, this tree symbol, transmitted symbol of n minus 1, n minus 2, and also what was the theta of n. After you have the theta of n and this tree, then you can distinguish if 1 comes when you are going, if minus 1 comes where you are going. Here you do not have something like this. Here, please take the point. Here, the L was 2. Here, L is infinite number. Okay, go for k is equal to 2. We want to go for the second step. Okay, I just showed, okay, when 1 comes, the blue branch, outcome of coming 1. The red one shows the minus 1 comes. You are here. When 1 comes, you go for 1, 1. When minus 1 comes, we go for 1, minus 1. Most recent at the most right. Minus 1, 1 comes, go to minus 1, 1, and you are at the minus 1. Minus 1 comes, you go to the minus 1, minus 1. Do we have any theta of n here? No. Why? Because we mentioned that theta of n comes inside for k is equal or greater than 4. Because the first 3 are inside the first step. After that, the first one goes to the second part, theta of n, and build up the phase for us. Okay. Some help. W12. Please don't disappoint me. W12. Here, this one. R2 minus the distance between the received symbol at the step 2, the second one. Between the transmitted symbol. Okay, you have 1, 1. CPM signaling. What's your transmitted symbol? E to the J, pi,
Q1
plus Q2. Thanks. Okay? This is W11. W1, sorry, 1, 2, 1, yes. 2, 2.
R2 minus E to J I Q1, no, minus Q1 plus Q2.
Minus Q1 plus Q2. The most recent goes for the Q1, the lowercase. Remember, it was 3T, Q of T. Remember we mentioned something like this, sampling. N of S is 1. I mentioned that you can go for the Viterbi diagram for N of S greater than 1 also. You have done it for 2, I remember. The performance will be much better. Not that much, but we can go on for the maximum MRC receiver. Will be better, by the way. Anyway, this one was the Q1, this one was the Q2, this one was the Q3. Okay? Remember, the lower one, the smaller one will be multiplied by the most recent. Q1, the most recent. The most recent here is minus 1. Q22, the last one, was plus. And also W3 and 2 would be R2 minus JE. Q1, the most recent for W3 and 2 is 1 minus Q2. And also W4 and 2 would be R2 e to the minus J pi minus or minus Q1 plus Q2.
Minus Q.
Minus here.
Oh,
Both of them minus.
yeah.
Oh, that's fine. This is, and also, I forget to say, I remember the last time also here, I just forget to this one too. Because the W, this state, comes from this state, or these two, W11 also need to be added. These two, W21 need to be added. And this is the power of the sequence detection. Okay, you need to be careful about, okay, what was the source of the state that I'm here? What was the source state? I need to be careful about the weight of that one too. If it was just this one, this is the maximum likelihood detection. Plus this one is the maximum likelihood sequence detection. Okay? Just be careful. Point is, here in this presentation I'm using the lowercase s. Could you please, to everyone to have one. This is the state diagram, state table for the complete GMSK signaling for the implementation of the receiver. You see that the uppercase S is something else. For the K greater than 5, equal or greater than 5, you're using the state table. But before that, we need to go over somehow outside the loop, manually, whatever, because it's different. Okay, K is equal to 3. We come up with this. We know what is the W12, 22, 32, and 42. We know what is the state. Now we need to go for the next one. We are expanding still. We are expanding until we come up with the structure that lets us to distinguish. We have here 3, that's fine, but there's still no theta. You need to know which theta, because for the next one the theta comes in 2. Still here we do not have theta of n because it's 3 and nothing before. Okay. I don't want to just write down all of the possible values here. I write it, but I want to just you to help me to write something like W23. W23. R3. Remember? R3. Each step the received symbol. This one is received. What's supposed to be transmitted when you are at step 1, 1 minus 1? E to the J, I,
minus Q1.
Thanks. Plus Q2 plus Q3. It was the transmitted symbol. The distance between the received symbol and transmitted symbol if this was transmitted. And if you are at that step, plus what?
W12.
W12. Perfect. For the W13 also, you need to add the W12. And also, you see, for the W1312, same things. For different possible value of transmitted symbol, for this one, finally this. Okay, we have accomplished the step 3. We have all the possible value of weights. You see the difference? Because we are expanding the behavior diagram, we do not need to delete anything, because the incoming branch to each step is 1. But for the k is equal to 5 or more, we do not want to expand, because if we expand the behavior diagram again, we are doing the sequence detection without minimizing the number of search. Therefore, we expanded until k is equal to 4. After that, 32 step. No expansion, deleting. Okay. For k is equal to 4, upper part and lower part. Now we have the theta of n. I wrote it that when you go to the step 4 here, the uppercase of the Viterbi diagram will be something like this, and the lowercase. But the point is that this 8 possible value of this tree, you see that this is 3, then 8 state, but there is a theta over here too. You can see at the state table that I brought to you, all possible value of each of those 8 states that belongs to the specific theta of n will be common in something like this. I n q1 plus I n minus 1 q2 plus I n minus 2 q3. 8 possible value of this, but the things that it differs is this one. For those who belongs to the theta of n equal to 0, when you want to build the signal, it means that the theta part was 0. Then you just need to put 0 here. Then this is the transmitted symbols. Okay? Just please look at here. You are here. 1 comes. What would be the transmitted signal? Okay? Therefore, it means that the sequence of transmitted symbol I was 1, 1, 1, and 1. Okay, I'm asking you to create the transmitted symbol for the GMSK. And you're saying that that's fine. The phi of t and I is pi q1 plus q2 plus q3. The formulation of the plus the second part, because now we have this one too. This one comes pi over 2 multiplied by this beautiful one. It will be the phi. Then the transmitted symbol will be equal to the j pi q1 plus q2 plus q3 to a to the j pi over 2. This is the transmitted symbol. Okay, therefore, when you are here, because all of these possible value of the first is 1, all of them goes to the pi over 2. And the other part, look at this one. 1 comes, goes to 1, 1, 1. This is 1 minus 1. When 1 comes, this goes to 1 minus 1, 1. It will shift these two, shifted to the first. It will be 1 minus 1, and 1 comes 1. This one makes this. No, at step 4, for the uppercase, we know that there is 2 possible values of theta. The first one is pi over 2. The second one, for the second one, the pi is minus pi over 2. Because here, minus 1, minus 1, minus 1, minus 1. These 4 minus 1 will be multiplied by pi over 2 and make this face. Now, because we have the second part, we can use the state tables. Go and look at the state table for pi over 2 and pi minus over 2, exactly the same thing. But still, VRIK is equal to 4. We do not have. But the point is that I start to number those. I suppose that it's up to you, it's up to everyone who want to implement the Viterbi diagram to consider, okay, the theta 0 is 0 theta for the first part. The theta of second is pi over 2 minus pi over 2. What was the second? Third of, yes, minus pi over 2. And last one, pi. Then you just can start to number. Okay, I consider the first symbol of this one, S1 through S8, S9 through S16, S17 through S27, and S25 to S32. Okay, well, that's fine. This one represented by till minus 1, minus 1, minus 1, and this face. After that, if 1 comes, you are here. Okay? You are, for example, in what step? Suppose that you are in minus. You are here. You are at theta is equal to 0 in the middle of the Viterbi diagram. Okay? You are at theta is equal to 0 on this. 1 comes.
Minus.
You will go to theta over of
Yeah.
what?
Minus pi.
Yeah.
Minus pi. Perfect. Because this one goes out. This one builds the pi. Minus pi over 2. And again, minus pi over 2. But this one goes to a state of
1 minus 1,
1 minus 1, 1. Perfect. And 1 minus 1, minus 1. Okay. You are at S step. What? What was the number of this one? This is 4 and this is 5, I believe. S5. Okay?
So this will be constant for AWGN.
Yes. For k is equal to, I want to explain two of the columns that you do not know what it is. The incoming state and the goes.
Yeah, it's that you can only go to.
Yes, you can go to two because two possible, but which one? Okay, I want to show you how to calculate that one. This is that I bring it to you, but the concept is here. Okay, you are at state 5. Okay, state 5 is for the theta is equal to 0. This is 1. Am I right? Let me see. Minus 1, 1, minus 1, of course. 5. Oh, 6. And the point is, I just shifted it. Actually, it's 5, but when you consider it, this one is 1, this would be a 6. That's fine. You're good. Okay, you're here. Now, without looking at the table, please, what would be this state? Minus pi over 2, the state of minus pi over 2 start from S17. Okay, therefore, 1, 1, 1 would be S17. Minus 1, 1, 1, 18. 1 minus 1, 1, which is this one, would be S17, 18, 19. Am I right? Let me see. Okay, goes to.
No.
Yes.
Yes.
19. Look at the table. Why state 19? Because this one is 17, this one is 18, this one is 19. Because you have 1 minus 1, 1. Look at the table for minus pi over 2. And for this one, actually, when this one goes to state 19, this one goes to state 20. The next one. You do not need this column, but the most important is comes from. Because when you want to start deleting at k is equal to 4, you need to, okay, the input branches to states, for example, whatever, you need to know from which state they comes. The last table, the last column, I mean, is important for you. You need this part. You need this column for implementation. Okay? Any question? Okay. An example is here again. Suppose that you want to just calculate the W14. Okay? W14 would be R4 minus, now we can use the state, the table. Of course, it's fine for you to create these S1 and S2 outside the Viterbi diagram, outside the loop, sorry. Because you need a loop, I will show you the structure of the program that you need to implement. You need a loop, but you do not need to, for every time, just at each loop, construct the S, because all possible values 32, nothing else. Go build it outside of the loop. Now, R4, you are here, the first one, build this one with this space, it's easy, it's this one, which is actually state 9. State 9 from the state table, and for example, W5, where is the 5 one? This one. This comes from this one should be 3T, that's wrong. I'm afraid that I will make it last time. This one comes from W13, therefore it will be added to this part, but this one should be added to this W3 tree. Because 5, 4, when 1 comes, it comes from W3. And same thing for the lower parts. Okay? Same thing. Just you need to use the state from S17 to S24 from the table that I brought to you. I post the table at the canvas today. Okay, now main loop. We have all 32 state available. You can build it, or you can use the state table. You need to build it in the MATLAB. That's fine, easy to build. Each state has 2 incoming and 2 outgoing branches. 2 outgoing branches, not important. But 2 incoming branches, you need to delete 1. Okay. Each state belongs to a specific theta. Possible value 0, pi over 2, minus pi over 2, and pi. And you know that if 1 comes, you go to those state which belongs to theta plus pi over 2, and if minus 1 comes, you will go to those state belongs to pi minus theta minus pi over 2. And also you know that if you was at the state ik minus 2, ik minus 1, ik, you will go to ik minus 1, ik, sorry, again, these 2 should be k. 1 again, ik minus 1. Writing the equations in the PowerPoint was a little bit difficult. It's not AWGN, I don't know. They need to use the same code, I don't know why. Word is simple, but PowerPoint. Anyway, ik minus 1, ik 1. This one goes here, this one goes here, and 1 comes 1. And ik minus 1, ik, sorry, and minus 1. If 1 minus 1 comes. Then you know exactly how to, where you're coming from, where you need to go. And also you know that the incoming branches to each state is what? Okay. Pi over 2. Use your table, please. And let me know you are at this state. When 1 comes, we are going to which state? Let me have mine. Pi over 2, pi, minus 1, 1. Perfect, 31. Yes. And of course, you go to whatever. When minus 1 comes, 32. Same as the... Okay. And this one is also 1 and minus 1 comes, but could you please give me the incoming branch of this state? Which branches? Do not look at your table, please. Just this one is very important. Okay. Just give me the theta and s incoming. First of all, which symbol come when you are here? Which outcome happened then you are here? It was one of the possible 32 states. An outcome happens.
When 1 came.
When 1 came. When 1 came, and okay, what was the possible theta of those states? You want to squeeze. When you say that when 1 came, you threw away 32 over 2, which is 16th of those states away. Okay? Now, which possible theta? Which possible thetas?
Could be either pi over 2 or 0. Or no, minus pi over 2.
Minus pi over 2.
Perfect. the possible value is pi over 2 and minus pi over 2. Then you threw away half of those 16. How many that we have? 8. We need 2, you have 8. And those would be this deleted by this, actually 2. Okay. Come on guys, it's very simple. It's not that hard. You was at pi over 2. Okay?
So minus 1.
It was a minus 1?
1.
The point, you have these 2 here. Okay? You have these 2. These 2, 1 and minus 1 was here. When 1 comes, these 2 move to some here.
Should be 1.
Okay. It should be?
It should be 1.
1. Because it was 1, it will be added. The pi over 2 to pi over 2, pi. And also minus 1, 1, minus 1. State 27. Look at the table. State 27 comes from state 10 and state 22. Is it 10? Is it 10?
Yep.
What about this one? Minus pi over 2.
Yep.
22? Then you need these. You need these column for implementation. The comes from column. Not the those 2, but the comes from column is important for you. And this is the loop. The main loop. For k is equal to 5 to n, do what? Go to another loop. For n is equal to 1 to 32, do what? First of all, calculate. Sm will be from S1 to S32. For each of them, you need to calculate these 2. And why you need the column of comes from? Because you need this one, the first one, comes from the incoming table. M, the first. This one is the incoming. By this incoming means the column of comes from. Okay? Just need to this indexing. I'm writing the code actually for you. I'm writing a part out. So, okay? You need this W. You need this W for creating the D1 and D2. And this is the Sm. Okay? You just need to compare this one, because what actually you need to do is go on till step n, calculate all of the weight for all of the possible states, and finally find the minimum weight and go back. But when you go back, if it was 2, you will be somehow confused. Then you need to delete 1, delete some. This is the actual point of the vector. Yeah, I explained it to you last time. When you know that this one is better than this one, omit it, go. You do not need that because this one is better. Therefore, this is not the optimum solution. D1 is better than D2, delete it. Delete the T2, D2. It's not the optimum. Okay, you calculate D1 and D2 and consider the W of S of M at step K is this minimum. But the point is that you need the most important and the most difficult part is to saving the winner state number. The point is that, okay, what was the winner state number? It was this one, or this one. If you choose wrong, if you address wrong, beta rate 50%. You need, because when you are at the state, when you are coming back, you need to go for the actual answer. If you address wrongly here, continue this procedure. Therefore, what you actually, again, like the maximum likelihood sequence detection for the system with memory, not the GMSK one, you need to create a W, which is a matrix of weights. W, let's call it 32 plus n, and also an index matrix, which also be 32. The first four of this n, these matrices, you need to put the number outside the loop because it's growing the viterbi. Each step has different number of states. You cannot using 4 or something like that. But I calculated outside the loop. But this one and also this one. But for k is equal to 5 or greater to n, you need this to create this one, use the last, go for, find the minimum for n, which is the last step. Which one is the minimum? Select that one, and you will have something like this. And Terrellist diagram where each state, I don't know, has one incoming branch. Maybe some has 2 outgoing, that's fine. But each has one incoming branch. And this one is the minimum. Now we need to go backwards. This state, for example, this is supposed to be connected to somewhere like this. This is the minimum. This one, this one, this one, this one are your answer. But the point is, each of them has 3 ik. Minus 2, minus 1, ik. Exactly, you know that this ik minus 1, let's call it in minus 1, in minus 2. This in minus 1 is here. Exactly here. You select this one. You select this one. Here you have IA minus 4, IN minus 3, IN minus 2. Select this one, go on. And you have your sequence. I know that it's a little, not little, it's the most complicated part of your course. Believe me. Even for the AWGN, that's simpler. It's much more the thing that we had last session. But because of the CPM, because the length of the filter is infinite, it caused some problem. And this is what we have inferred something like 15 years ago. I built the GMSK receiver. It was working perfectly, that's fine, believe me. And you can go for something of like this, a bit of rate. 10 to the minus 5 for SNR 10. Bring it to me, you have your point. Do not expect something specific at your project, explanation, so on, documents, but I need your codes. If you have problem, come to me, ask. We need to solve it. You need to, come to me, and if there is any question, I will be glad to help you. I don't want to say that, but if you do not finalize your project, that's okay. But believe me, you will lose because it's a great thing. I give you an example. Recently, for example, IEEE 802.15 plus 6 or 16, I don't know. the standard that they established for the body area network has the GMSK on it. The modulation is the GMSK. It's not, you see, the point is very important. The power of the GMSK signal is not just because of the AWGN channel. It's worked perfectly at the wireless channel. Maybe you say that, okay, the performance, the binary QST is a little bit better than this. I accept, it's better, but not for the wireless channel. Because the information is at phase, changing of the phase. And also the properties of the spectrum of the transmitted signal, which was the other motivation for us to using the signaling with memory, is very important. The last thing, just I want to ask you a question. What do you think? What is the, you see, these three, specifically this one, are vulnerable to have error on that. Any idea? The point is that in actual system, for example, the GMSK, they put the data here. This is 158. They put the data here, but they put a training sequence of 3-1 here, 3-1 here. Why? Because when they are here, because you are not deciding actually of IN here, you're deciding of IN minus 2 here. Because the transmitted symbol contains Q1 IN, Q2 IN minus 1, and Q3 is minus 2. Okay? Which is the great part? Which is the greatest between this one, and this one? The portion of this one is much more than the others. Because the Q of t is something like this. This is a little, something like 1 over point. You will go to error. Therefore, you need to go 3 other steps. But the point is that you know what are these 3. It will also help you to decide it perfectly. It also helps to also this one too. You know what is the start of the states. You know what is the income. You know what is the outcome. You force your vector diagram to go to this state at last. You're forcing it. And enforcing it. You do not need to implement this procedure just for your information that by this maybe you see that at your simulation the last symbols are goes to error because of this, because you are transmitting a little part of the transmitted symbol inside that, which could be destructed easily, but this one not. This one is a bigger portion. If you want to go and delete the other, you need to go for 2 or 3 steps forward. As I mentioned, I'm not going to ask you to solve anything of the GMSK at your exam. We will have an example of maximum likelihood sequence estimation or detection. Exactly the same of the example that I've solved for you, maybe just changing the alpha 1, alpha 2. That's it. But for this part, I will ask you a question about those points, the number of states, I don't know, something like that. 2, 4, 7 again. The other 2. There is no guarantee that you can also accomplish with the project, even you're here. I don't know how they want to accomplish the project. I decided to extend 1 week because the due date was next. Anyone start the simulation of the transmitter?
Yeah.
Any result?
I got for n equals to value.
No, I mean any result. I mean that I prepared an information for you. I mean a sequence of data 32 bits, and I also prepared the INQ for that. Same result.
Not quite. I'm
Oh,
still
my.
figuring it out.
You can come and ask me.
Yeah.
You can come and ask me.
So I guess one of the big questions for when I was simulating it was, you give us Q as like, I don't know, 30 something.
24.
Yeah,
24.
So it's 24 long. Do we just select like every four?
Not for the transmission. For the transmission part, I explained it.
Yeah.
Also already. For the transmission, I want to see that you can handle this one. It's completely simple.
Okay.
Because instead of, for example, instead of I and Q1, you have this Q1 to Q8. This one to this one, first sample. This one to this one, second sample. This one to this one, and so on. Just remember this figure. I always, for example, you want to add. Sorry. T, 2T, 3T. For example, we want a signal of this part. You are for the first, third, the second. You have these three signals.
Yep.
And you need to add this port, this port, this port, and this port. Also multiplied by A. You can sample 1, you can sample 8. For the transmission, I asked you for 8. And the shapes, the figures that I prepared for you is based on the 8. You can see that the number of samples is 256. But for the receiver, select your Q1 actually would be Q4, the fourth. You can go for the first. And this one gives you a little bit better.
Yeah, because they were sampling halfway in the middle.
Yes. But spectrum will be a little bit more. You cannot see it, but it is if you use just one and specifically middle. But the performance is a little bit better. Q2 would be, just Q2 would be 8 plus 4.
Yep.
Plus 4. Q3.
Okay.
Select those and start the simulation of the receiver. Any question come to me. I will be glad to help you. You just need to, the videos of this session and the last one, just I need to.
That would be more easy for us.